Well, good afternoon. It's 2:35, 5 minutes late getting started on Wednesday, the 12th of February, 2020. It's supposed to be differential equations class, but the sad news is I'm the only one in the room. So let's go on and get started from the current slide. If anyone does come in, I'll go over announcements at that point. So where we left off last time, I can hardly speak. I don't know what's the problem. Was in Chapter 2, First Order Differential Equations, 2.2 Separable Equations, and we got down to the bottom of page 49, and they're talking about losing a solution, which is a weird way to express an example. But anyway, here's what we had. I'm not going to redo everything we did, but I will give you at least a perspective of where to get started. Here was our original, here was example 3, the differential equation. dy dx is equal to y squared minus 4. Okay? Now, of course, to separate variables, we would do dy over y squared minus 4 is equal to dx. Okay. Now, we started off the process of saying, and I was real tempted to say this all along the way here. It's obvious as soon as you do this that y cannot equal plus or minus 2. But you see, y could equal plus or minus 2 up here, then it just means that your derivative is 0, which is okay. It's all right to have a derivative of 0. But when you go to separate variables, you now lose those two possibilities of y is equal to plus or minus 2. Okay, just by the way you've done this. Now, how we proceeded was to do this, and we were doing a partial fractions, and I'll get down to where we got there. I believe it was, I'm going to go back and I won't fill in all the gaps, but I'll fill in some. It was 1/4 the integral of dy over y minus 2 minus 1/4 the integral of dy over y plus 2 okay, is equal to the integral of dx. Okay, that's what it turned out being when we did our partial fractions. And what this gave us was 1/4 the log of absolute value y minus 2 minus 1/4 the log sorry about that, of absolute value y plus 2. And that's equal to x plus some constant c. They call it C1. Okay? I'll call it that just for fun. Okay? Now, just wanted to point out something else you've lost as soon as you did that. When you got logs, okay, we put absolute values around, and I guess that takes care of it, but you see, logs can never be, the argument of log can never be negative. It can't be 0, of course. We've already thrown out the plus or minus 2, but it also can't be negative, but we put absolute values on, so we probably can still deal with those. All right. Now, I think at this point, this is about where we left off last time. And here's what I would suggest that we do next. Factor out the 1/4. Okay. Actually, better than that. Let's just multiply everything on both sides by 4. Okay, almost everything. Okay, so that gives you log of absolute value y minus 2 minus the log of absolute value y plus 2 is equal to 4 plus some other constant. They call it C2. 4 times C1 is C2. It doesn't matter. They're just constants, so we don't need 4C1. We'll just call it C2. Okay. Now, what this suggests, by the rule of logarithms, is that the log of y minus 2 over absolute value y plus 2 is equal to 4 plus that C2. All right. Now, what we're going to do now is e raised to the exponent both sides of the equation. Okay? Now, and in doing that, and by the way, the absolute value is numerator and denominator, you can just put one absolute value. So that's the, if you e both sides, that just gives you now they do two steps at once, and I guess I should just to do what they did. But I think I will step it out for you. Let's do an e on both sides. Okay, I'll do it that way. Well, e of a log is absolute value y minus 2 over absolute value y plus 2 is equal to e to the 4 plus C2. Now, I'm going to change that. Wait. I left off an x. 4x. Yuck. 4x. And I'm going to go and write it because I'm tired of writing like this. This is e to the 4x times e to the C2, which is just some constant. We'll call that constant C. I'm going to put it in front there. Now, a little bit of a problem you have here is that absolute value bars. There is absolutely, if that ratio is positive, everything's hunky-dory. But the if it's negative, E is never negative, so you'd have to have C being negative then. So I don't see why we don't leave that, but what I'm going to do is just make this y minus 2 over y plus 2 is equal to CE to the 4x. Now, there is some problem there. What if they were negative? Well, then that allows the C to be negative. So I think we're okay with that. Now, here they do, no. All right. I think we've got to carry around the plus or minus, okay? Just to be consistent with what they do. They don't ever quite say why, but it is. I mean, that ratio, when you E both sides, E to something or another is always positive, and because this ratio could be negative, we have to have a plus or minus there. Now, of course, the C could be plus or minus, but that's we're going to assume C is positive here. Now, what we're going to do next is try to solve for y. This is an implicit solution. We're going to try to make it explicit. So So what we're going to do is multiply both sides of the equation by y plus 2. So you have y minus 2 is equal to y plus 2 times c e to the 4x. Okay? Understanding it's a plus or a minus there. Okay? So let's multiply through, and you have y minus 2 is equal to cy e to the 4x. Okay. And remember, you got plus or minus. I don't really think we need that, but we'll see. Plus 2c e to the 4x. Okay? All right, let's carry on. Let's multiply. Oh yeah, we've done that. Okay. Now, let's gather all of our y's together. So this will be y minus c y e to the 4x. When you subtract that from both sides, and over here you'll have 2 plus 2c e to the 4x. Okay? Now, let's factor out the y here, and you have y times 1 minus c e to the 4x is equal to, factor out the 2 here, 2 times 1 plus c e to the 4x. And then merely divide both sides by 1 minus c e to the 4x. I can't write. Okay. And there you have your solution. The one that they have here is y is equal to 2 times 1 plus c e to the 4x over 1 minus c e to the 4x. Okay. And there is the solution they have. Now if we factor the right-hand side of the differential equation, we know from the discussion of critical points in section 2.1 that y is equal to and y is equal minus 2 are two constant or equilibrium solutions. That's what we were saying before. The solution to y is equal to 2 is a member of the family defined by this. Okay. However, y is equal to minus 2 is a singular solution. Okay. It cannot be obtained from this. Okay. So y is equal to 2 and y is equal to minus 2. That certainly gives you places where your derivative is 0. This can be gotten from that because when you let, say, x equal 0, you get, that would be a 1 plus 1, which would, a 1 plus c over 2 times 1 plus c over 1 minus c. And for the value c equals 0, then that gives you y is equal to 2, which is fine. And that's why they say that does give you part of your family of solutions. But you can never get the minus 2 in there, okay? And that then would be a singular solution. So that would, if you basically lost it in the solution process, because as soon as you divided here, you basically ruled out that possibility, okay? And I don't know why they make such a big deal of it, but this is your solution, but realizing that you have a singular solution that you can't get from there, okay? That's the bottom line. We usually don't worry about those kinds of things too much. Perhaps we should. We're just looking for solutions. And this gives you the vast majority missing that one, okay? And you can get that from the very first, saying, yeah, y is equal plus or minus 2, give you your equilibrium solutions. So you know it's got to be a solution. Okay. Now, moving on to example 4, an initial value problem. It says solve this. E to the 2y minus y times cosine x dy dx is equal to e to the y sine 2x. Okay, there's your differential equation, your boundary value. Since this is first order differential equation, you need one boundary condition, and this one happens to be y at 0 is equal to 0. So the point 0, 0 should be on your solution curve. Now, pretty hairy looking problem, definitely not a linear problem. It's a separable problem, which should be, in a sense, fairly easy to evaluate. So what we do is divide both sides. Well, we got y's here and y's there, so what we're going to do is divide this side by cosine x and this side by cosine x. Divide this side by e to the y, and you'll be dividing this by e to the y. Okay? These go out, and then we'll write it in differential form. And what you have is e Okay, I'm going to simplify this a little bit as I go. Okay, well, I could have left that e there, but I erased it before I thought about it. E to the 2y divided by e to the y is e to the y. Same base, different exponents, dividing, subtract your exponent. 2y minus y is y. Okay, minus, and here we have y times e to the minus y. Okay? I'm writing it in that form just because I think it's going to be easier to deal with later. And this is all multiplied by dy. Okay? And over here, again, let's figure out what sine 2x is. Okay? I don't know if you remember your double angle formula, but this is 2 times sine x cosine x. Okay? I don't know if these are in your book or not. I think they are, now that I think about it. Well, maybe not. There's derivatives in there, but I don't know if they have the cosine, the sine identities. I don't see them. But that doesn't mean they're not here. Let's see if I can find any other. But you can look this up anywhere you want to. It's from your double angle formula that sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. If alpha and beta are the same, then you have sine alpha cosine beta plus sine alpha cosine alpha plus sine alpha cosine alpha, which is 2 sine alpha cosine alpha, which is If you have x's there, you have this. So instead of this, you have that, and here you can divide out a cosine x. So you're left with 2 times sine x dx. Okay. Now hopefully none of the things you did there are necessarily going to cause you any pain later. Certainly dividing by e to the y isn't going to cause any effort because e to the y is never 0. Dividing by cosine x, though, could be, because at all values x, where x is any of your half pi's, these are not defined. You know, you can't do that because you'd be dividing by 0. But you see, your initial condition is y of 0 is 0, so you're not even close to a half pi. But you've got to be between negative pi halves and pi halves. So you are, this sets your interval for you. The fact that you divided by cosine x basically sets the interval for you. All right, so let's see if we can integrate this. Integrate both sides. Okay. Now here I can do that one, e to the y. Okay, that was pretty easy. Minus the interval of y e to the minus y dy. Okay, and this is equal to 2 times the antiderivative of sine x is minus cosine x. Okay, so I'm going to put the minus out front and just make it cosine x. Okay, and then you have somewhere out here a plus c, and we may change that to something else later, but we're okay with it now. Okay, now we've still got this integral to go. Now this is Cal 2, but using your Cal 2, if you remember, this is integration by parts. Okay, where you have a product of two functions, and taking the derivative of one will make it simpler. Antiderivative of the other doesn't make it any more complicated. So what we'll do is let y, I'm trying to think how we used to say it. I guess v is equal to y. Let v equal y, and dv is equal to e to the minus y dy. Okay, then dv is equal to dy, and v is equal to, when you integrate that, you get a minus e to the minus, well, I'm integrating it, all right, minus e to the minus y. Okay. Now, if you want to check that, just take a derivative of it, and you get minus e to the minus y times minus, which is plus e to the minus y. So yeah, that works okay too. So what's the result of this? Then you take your uv, oh, that's what I wrote wrong. This is u, and those are v's, I'm sorry. Duh. All right, your uv is then y minus y e to the minus y plus, because it's a minus, the integral of v du, which is e to the minus y dy. Okay? Now watch these minus signs. There's so many of them in here. It's so easy to get tripped up. Okay, and there's a minus out in front of all this, so that's going to change both signs. But anyway, you get e to the y minus a minus is plus y e to the minus y. Okay, and then when you integrate this, it's minus a plus, which is a minus, but when you integrate that, you get plus e to the minus y. Okay? Is equal to minus 2 cosine x plus c. Okay? Now we plug in our initial value, y of 0 equals 0. Okay? Well, e to the 0 is 1 plus 0 plus 1 is equal to minus 2, and cosine of 0 is 1, so it's just minus 2 plus c. So add 2 to both sides. I think you get c is equal to 4. Okay? So let's go back and plug that in, and what we have is e to the y plus y e to the minus y plus e to the minus y is equal to 2 minus 2 cosine x plus 4. Okay, I hope that's right. Let's see what they got. E to the y plus y e to the minus y plus e to the minus y is equal to, and then they reverse the order and said 4 minus 2 cosine x. Exactly. Okay. Now, this puts you, and they show the level curves for this, it puts you on that one in the center that goes through 0, 0, because that's your initial condition. So that's your level curve here. And that's for c is equal to 4. C is equal to 2 is down below. So this is the solution for that. Now, the next little blurb they have here is use of computers. They say that in the remarks at the end of section 1.1 mention that it may be difficult to use an implicit solution to find an explicit solution. And this one is one of those cases. There's just no way you're going to be able to isolate the y there, I don't think. Okay? So it says solutions like this are frustrating, I guess, somewhat frustrating. I'm just seeing, I mean, this is just more blah, blah, blah. They go on and on about it, but I really can't see too much value in trying to track it down. And they do some playing around with something, so maybe we should, just for the benefit of having done it. They give you an initial value, or suggest there's an initial value, initial condition, leading to a particular solution by yielding a specific value of the parameter c in a family of solutions, first-order differential equation. There's a natural inclination for most students and instructors to relax and be content. However, a solution of where this is heading However, a solution of the initial value problem might not be unique. So this is back in example 4 of section 1.2, as if we didn't have enough of this. Here's what we got. dy dx is equal to x y to the 1/2 power. And we had initial condition of y of 0 is equal to 0. Okay. Now they say it has at least two solutions. Y is equal to 0 certainly would work because d0 dx is 0 and okay. Certainly when y is equal to 0, dy dx is 0, and x times the square root of 0 is 0, so that's 0. So that works. Now the other solution that they said is y is equal to 1/16 x to the 4th. Okay, well, let's see what happens there. dy dx would be 1/4 x cubed, so that's on the left-hand side. On the right-hand side, you have x times, and when you take the square root of x, you get 1/4 x squared, and x times that would be 1/4 x cubed, which is exactly what you got for your derivative. So both of these do have solutions, and that would be fit the initial condition, has a solution there. Now, let's see if we can solve this. They just gave us those. Let's see if we can solve it. What you would do would be dy over y to the 1/2 is equal to x dx. Okay. No. Okay. Yuck. I don't pay close attention. My pen drags. All right. Now, I've kind of messed up a little in my writing. I don't know why I was starting to put T's in there. That's what it looks like. And these are X's. Okay. Yeah. Okay. I need to take a quick break. I've had a little bit of stomach issues today, so I'm going to pause this for a moment. I'm sorry I had to take that break. I was just feeling a little sick, and I had a can of soda in my office, so I took a swig of that and feeling a little bit better now. And then on my way back, I realized since still no students are here, I was counting on a student showing up. To keep up with time for me, I'd better bring my phone that has a clock on it, so because my watch, the battery died, and the computer doesn't indicate the time. So anyway, here is the what we have for our separation of variables in this equation. Now, in order to do this, I think I prefer to write this as y to the minus 1/2 dy is equal to x dx. Okay. Now we integrate both sides, and that gives us okay. If you think about this, this is going to wind up being I'm just going to write it down. 2 y to the 1/2, that is ugly too, okay, is equal to x squared over 2 plus c. Okay. Take a derivative of that, of the left-hand side. 1/2 times 2 is 1 times y to the minus 1/2. That's exactly what you've got there. I'll try to make that 2 look a little better, and I've disappeared it altogether. Okay, there we go. And there's what we've got. Now, you take that, let's multiply both sides by 2, and you get 4 y to the 1/2 is equal to x squared plus, and let's just still call it c, even though it's twice c, but yeah, it's just some constant. Okay. Now, if you're trying to solve for y, make an explicit solution, divide everything by 4, and that gives you y to the 1/2 is equal to x squared plus c over 4. And then if you square both sides, y is equal to this is a bit bizarre. Again, the C can take, oh yuck, my screen just went off. I don't know why it does this. There's something about, I don't know if my, here it's coming back finally. Well, it's trying to come back. Okay, here we go. Okay, the C doesn't matter. You could make this as to be I should have done that. You could make this to be x squared over 4 plus some other constant c. I mean, just anything, okay? And then you square both sides, okay, to get your y, and this will be x to the 4th over 16 plus some other constant c, okay? Doesn't matter. It's just a number out there, okay? And that's where they get their, I know, I guess that last time they did need to square that. So, they're throwing in all sorts of things here, like trivial solution, okay. This is the solution they get. Okay. Sorry. I was trying to do too much with, okay. Okay, y to the 1/2 was equal to that, so then you square this and you get y is equal to 1/4 x squared plus c squared. And that's the solution they got. 1/4 x squared plus c squared. Okay. Now, and as they were saying before, there's no way, so when you set x equals 0 and say that y has to be 0, that would indicate that c has to be 0. Okay? Yeah. Therefore, x equal 1/16 x fourth, that's the solution we got from that. Okay, because when you square this with c equals 0 that you get from your initial condition, you get 1/16 x to the fourth. And that's the solution you got up here. Now, that's a solution to your initial value problem. However, your trivial solution, well, of course, when x equals 0, y is equal to 0, so that works for that one as well. However, they say that one was lost by dividing by y to the 1/2 when you came here. And of course, this would preclude that because you can't divide by that. So that's where you lost the trivial solution, because you can't do that. However, if you plug it back in, y is equal to 0 works when x equals 0, so it is sort of 1. Okay? And then they introduced this other concept of plugging in any value a, where you have x squared minus a squared squared, which I don't know particularly where that came from. For a is positive, then that seems to work as well. Okay? But again, there's I really don't see the point of chasing that rabbit any further. Now, the next issue here is your middle of 51, and that is your integral defined function. And again, they talk about one of the remarks at the end of section 1.1. It's pointed out that for certain differential equation, you may not get any better than just an integral defined function. Okay? And if that's the case, you're just sort of stuck there. And I think example 5 is going to illustrate that, so let me do that without going into all the rigmarole that they did leading up to it. Here's your situation. dy dx is equal to e to the minus x squared. Okay? And you do have an initial condition, y of 3 is equal to 5. Now, there's nothing too initial about it. You just have a fixed value there. Now, if you separate variables, you just have dy is equal to e to the minus x squared dx. And if you try to integrate both sides, you get y is equal to, whoa, a moment here, okay? There is no technique that we have to integrate that. There is just nothing you can do for that. So you go back to your fundamental theorem of calculus, part 2, I believe it is, and you make this the integral of from x sub 0, well, okay, they do it from 3 to x of e to the minus t squared dt. Okay, that's how you pretty much do this. Now, why the 3 down there? Because that was your initial condition that you know a value for. Okay, and when you plug in 3 for x, then this becomes 0. Well, let's see. Oh yeah, plus c. Left off my plus c. Okay, and when you plug in 3 for x, then that makes this go to 0, and your y has to be 5. So you wind up with y is equal to, and they for some reason like to put the constant in front, so we will, 5 plus the integral from 3 to x of e to the minus t squared dt. That's your integral defined function. Now, if you're at all familiar with it, this looks a lot like your, what do you call it? Bell curve, okay? It's something that's used in statistics a lot. Now, you would have to have a bunch of coefficients in front of it and other things, but yeah, that's exactly what you get, and you just basically have to plug in values to figure out what you need, okay? And so that is your solution. Y is equal to 5 plus the integral from 3 to x e to the minus t squared dt. Okay. Now, they do have a remark here at the end. In some of the preceding examples, we saw that the constant of one parameter family of solution for a first order differential equation can be relabeled when convenient, and we did a lot of that. And they go into some with arc tangents and stuff, and that just, I don't see no reason to chase those. So anyway, that finishes 2.2. Do any of the odds 1 through 21, do any of those who have answers in the back. Then do any of the odds 23 to 27 who have answers in the back. Do 29 if it answers in the back. 31 or 33 if those answers are in the back. 35 if its answers in the back. 37 if it is. Any of the odds 39, either 39 or 41 if those answers are in the back. 43 if its answers in the back, and any of the odds 45 to 49 if those answers are in the back. Now, I think you'll find most of them back there. Generally, the discussion problems do not have answers in the back, so I'm not going to suggest that you do much with those, because you can't check them anyway. But let's move on to 2.3, which is linear equations. Separation of variables, except for some of these weird things they brought up at the end, very straightforward. Sometimes you can't integrate, then you leave the integral in part of your solution. Sometimes it takes varying techniques. We used integration by parts on one, we used partial fractions on another. You may have to use any technique to find those integrals. And if nothing works, you leave your answer in an integral form. All right. So let's move on to linear equations. And first, I guess you have to define what in the world is a linear equation. As they say here, we continue our quest for solutions of first-order differential equations by next examining what we call linear equations. Linear differential equations are an especially friendly family of differential equations in that, given a linear equation, whether the first order or higher order, there is always a good possibility we can find some sort of solution of the equation that we can examine. So the form of a linear first-order differential equation was first given back in section 1.1, and here is a redefinition, I guess, of that. A first-order differential equation, I'm just going to put DE, of the form a sub 1 x dy dx plus a sub 0 as a function of x, y is equal to some function of x, g of x. Okay? Now, in this case, both of your coefficients are functions of x, may be functions of x, and the equation on the right-hand side is a function of x. Now, notice what you can't have. You can't have the dy dx raised to any power other than 1, and you can't have the y raised to any power other than 1. So you can't have a fractional power, you can't have a integral power other than 1, you can't have any other y dependence in that. You can't have a y that's not linear. In other words, cosine y wouldn't work, sine y wouldn't work, e to the y wouldn't work, because those are not linear, okay? On the right-hand side, g of x, just like your a sub 1 and a sub 2 of x, any functions of x. Sine x, e to the x, log x, doesn't matter, okay? But it does matter for the y's. That's a linear equation in the variable x. Now that's not quite in standard form though. So how do we get it in what we call standard form is divide everything on both sides of the equation by your a1 of x. This of course is assuming that a1 of x is not equal to 0. And if you do that, then you wind up with dy dx plus, now this is just some other function of x, let's rename it and call it p of x, okay? And then that's going to be multiplied by y, and this is going to be, what do they call it, f of x now. G of x divided by a1 of x, we'll just call it f of x, okay? Now, that's what we call standard form for a linear equation. Now, one thing not to do not assume that p of x is a polynomial function. I know capital P of x is often used for a polynomial function. It may be, that may be fine, but it doesn't have to be, okay? It's just some p of x, okay? Now, we seek a solution for that on some interval I for which both the coefficient functions p of x and f of x are continuous. So in other words, if that p of x was a rational function, and anytime that denominator did become 0, you got problems, okay? Because that wouldn't necessarily be, in fact, it probably wouldn't be, except in certain circumstances, continuous. And f, of course, also has to be continuous. So it says, before we can examine a general procedure for solving this, note that in some instances, that equation can be solved by separation of variables. Here are a couple of examples. Okay, what if we had dy dx plus 2xy equals 0. Now your p of x is 2x, your f of x is 0. Well, fairly obvious that can be solved by separation of variables. So what you would do would be subtract 2xy from both sides, and that would give you dy dx is equal to minus 2xy. Okay? Now divide both sides by y and write it in differential form, and you get dy over y is equal to minus 2x dx. Okay? and that is solvable. Okay, this would be log y, absolute value of y, is equal to minus x squared plus c. Okay? Now, if you don't believe that, take a derivative. What's the derivative of log y? 1 over y, dy. And what's the derivative of minus x squared? Minus 2x. Yep, that works. dx. Okay? Now, so that linear equation could be solved by separation of variables, and it wasn't hard to do. Okay? However, this one, let's see, I'll try it down here, dy dx is equal to y plus 5. It's also solvable by separation of variable. dy over y plus 5, I can't write, is equal to dx. Okay? And this would be the log of y plus 5 is equal to x plus c. Okay? And you can solve that one. Okay? It's both linear, separable. Okay? It's certainly a linear function. You could write this as dy dx. Can't write my dx. It won't write. I can't get it to write that near the bottom. But that's the dx down here. Okay? Minus y is equal to 5. So that's linear. The p of x is minus 1, the alpha of x is 5. Okay? And it's solvable by separation of variables. Okay? However, if you had this one, it doesn't look that much different. dy dx plus y is equal to x. Can you solve that by separation of variables? No, because that's plus or minus x plus or x minus y, and you can't separate that by division. Okay, and that's what's required for separation of variables. And yet that's a classic form of p of x be 1 and x be f of x. Yeah, that's a linear form. You cannot solve by separation of variables, but you can solve by what we're about to do, linear. Okay, I've got 4 minutes left, so don't try to hurry. Now, this method of solution, they take you round and round and round, and I'm going to try to simplify as much as possible and tell you what to worry about and what not to worry about. So, let's get started. I think I'll first write down my equation again, because I just erased what I had. So dy dx plus p of x y is equal to f of x. Okay, there's what we're starting with. Now the method for solving that hinges on what they say is a remarkable fact that the left-hand side of the equation can be recast into the form of an exact derivative of the product by multiplying both sides of this equation by a special function mu of x. So we're going to multiply both sides of this equation by a special function mu of x that's going to make the left-hand side a perfect derivative, exact derivative. Okay? So let's do and start that. Okay? So we got mu of x dy dx plus mu of x p of x y is equal to mu of x f of x. Okay. Now, I'm going to start leaving off the of x's most of the time. They do. And what we want this to be is we want this left-hand side to be a derivative of a product. Okay? And what that product is going to be mu of x times y. Okay? So we want this thing here to funnel down and be d by dx of mu of x, I'll go and write it, times y. That's what we want it to be. Okay? Now if you take a look at this and you were to do the product rule on this, this would be mu of x times derivative of y with respect to x plus y times the derivative of mu with respect to x. Okay? That's exactly that. Well, notice this first term is exactly what we've got. Okay? And we've got a y here on both of these. So all we need is for d mu dx to equal mu of x p of x. If we could get that to be true, then we've got it knocked. Okay? That is what we want. Now, that equation can be solved by separation of variables. Whether the first one could or not, immaterial. Okay? But this one can. Okay? So what we're going to do is d mu over mu is equal to p of x dx. Okay? And we're going to integrate both sides, and that gives us log of mu is equal to the integral of p of x dx. Okay. Now we know p of x. That was given to us in the very beginning. Okay? And what is your log then? Let's e both sides of that. Okay? And this gives you mu is equal to the e to the integral of p of x dx. Hey, if we know what p is, if it's an integrable function, and remember that was one of the requirements at the beginning, is that the p of x and f of x must be continuous functions if they're, well, let's see. You can't quite say if they're continuous, they've got to be integrable, but most of the time they are. So if p is an integrable function, then your mu of x is going to be e to the integral of px dx. Okay? That's it. If we can make that happen, we're okay. Okay? Now, that is what we call our integrating factor, because what are we going to do? We're going to take whatever that mu turns out to be and multiply both sides of the equation, everything on both sides of the equation by that, and that's going to guarantee us we get a perfect derivative on the left-hand side, and then we can fiddle with the right. Okay? Now, they come up with a really weird formula and then show it to you, work it out, and then emphasize that you should not memorize the formula. Okay? So here's the procedure that should be done. And I just went over by a minute. Okay? I'm going to stop here, and we are going to pick up from here next time. And we'll probably go back and pick up a little bit there, but that's where we're going to head. So anyway, we're out of time. Homework exercises on this. I don't know if you got far enough along. No, we didn't do any examples here. So all your homework is in 2.2, plenty there. We'll pick up with 2.3 next time. So let's get out.